Our experiment was split up into 6 smaller experiments, each to show an important behaviour of light. We used many of the screencasts provided on Khan Academy website and the provided lab manual to understand many of the properties of light we were testing for. Our setup for all the experiments was generally a microwave transmitter and a microwave receiver attached to a gonometer in some position. For experiment 1, we looked at the general behaviour of microwave light. Our experiment consisted of changing the distance and angle between the microwave transmitter and the receiver and recording the receiver value denoted in our results as M. For this experiment, the dial of the receiver remained on 10 times strength. Our first table of data shows how the intensity of light M varies with distance given as R from an emitted source. The values for distances were all in centimetres. Our second table shows the data recorded when the distance between the transmitter and receiver stayed at a constant value of 80 centimetres, and it was the angle between the receiver and the transmitter that was changed from 0 to 90 degrees each way. From the first table, we can see that the greater the distance between the source of light and its receiver, the lower the recorded value for intensity. The relationship seen in the experiment follows a rule of intensity equals 1 over the distance squared, which is also the inverse square law that all wavelengths of light follow in relation to distance. For the second table, we see that the receiver value M is greatest for the lowest change in angle between the receiver and the transmitter. Increasing this angle is inversely proportional to the intensity of light. This result is expected as the largest fraction of microwave light that will be recorded when the receiver's surface is perpendicular to the direction of the transmitted wave. Interestingly, when we slowly move the receiver towards the transmitter of the microwaves, the receiver value oscillates in intensity. Since microwaves can have wavelengths of up to a few centimetres, this effect could be explained by the transmitter picking up standing waves, further explained in experiment 3. When plotting the M values we had from before, over 1 over R, we see a linear relation. This shows that the M values we found are negatively proportional to the distance R, and that the M value is related to the electric field of the light. For experiment 2, we investigated the property of light reflection. Between our microwave transmitter and receiver on our setup, we placed a flat reflector plate. The angle between the incident wave from the transmitter and a line perpendicular from the reflector surface was adjusted to be exactly 45 degrees. By turning the reflecting mirror component to specific angles between 30 and 80 degrees, we measured receiver values shown as M in the table. As shown, the intensity of the light varies as the angle of incidence changes. The angle of incidence and reflection are directly related. The angle of incidence is always the angle of reflection and vice versa. This is an important law of reflection. Since our reflecting surface is relatively rough, the microwaves incident onto the surface can be hitting at many slightly different normals to the reflecting surface. This produces reflected waves travelling in many slightly different directions. In experiment 3, we wanted to calculate the wavelength of the emitted microwave light. We can do this in our experimental setup using properties of standing waves. Some of the microwaves that are emitted from the microwave transmitter will bounce back off of the microwave receiver and travel in the opposite direction. As seen in the picture, the points where the waves are not meeting are the antinodes. The wave in this region is fluctuating from the maximum of one wave to the minimum of the other. The points where the transmitted wave, shown in green, and the reflected wave, shown in blue, meet are the node points. These points are where the waves cancel out completely. We also see that the distance between two nodes is half the wavelength of the transmitted or reflected wave. In our experiment, we change the distance between the transmitter and the receiver and note how many times the receiver value oscillates. This will tell us how many nodes were present over that specific distance that we passed through. Calculated wavelength was found by dividing the distance travelled by half the number of nodes counted. From our data, we find that the microwaves used have a wavelength of 2.87 centimeters plus or minus 0.2 centimeters. The actual value for the microwaves, that is given in the lab manual, is within our range at 2.85 centimeters. For experiment 4, we investigated the properties of light refraction. We placed a prism filled with styrene pellets between the microwave transmitter and receiver. We found that the point where the microwave receiver has the highest receiver value was when the components were not directly facing each other. The highest intensity of microwave light appears to be at an angle of 14 degrees away from the incident path. Since the incident light hit the prism at 90 degrees head-on, there was no change in the light path when the light entered the prism. However, when the light exited the prism, it did so at an angle. This is a property of light refraction, where light will change direction slightly when meeting a material with a slightly different refractive index, as it will slow down or speed up depending on the material. Using Snell's law, taken from the Khan Academy website, we can calculate the refractive index of the styrene pellets. We assume N2 is 1, as this is the refractive index of a vacuum, and we calculated θ1 and θ2 from the provided angles. From this, we calculated the refractive index of the styrene pellets to be 1.49.
In experiment 5, we wanted to investigate polarization. The microwave radiation from the transmitter has an electric field which remains aligned with the axis of the transmitter's diode, and it is the orientation of this electric field that defines the radiation's polarization. We explored how using a polarizer can affect the orientation of this electric field. To do this, we recorded the radiation detected by the receiver when it was in the same orientation as the transmitter, and then rotated the receiver in increments of 10 degrees and recorded the radiation at the receiver during each step. We found that the receiver detected decreasing radiation until the receiver was oriented 90 degrees to the transmitter, at which there was 0 radiation detected. This was because at 90 degrees, the receiver was horizontally oriented and could not detect any of the vertically polarized radiation. After 90 degrees, the radiation starts increasing, showing the mirror effect to the first 90 degrees of rotation. At all angles other than 90 degrees, there is a vertical component to the alignment of the receiver which detects the vertically polarized radiation. Because this vertical component is smaller at angles closer to 90 degrees, there is less radiation detected at angles close to 90 degrees, and the radiation detected increases towards 0 degrees and 180 degrees. In the next section of experiment 5, we investigated the effects of a polarizer. To do this, the position of the receiver was reset to 0, and a polarizer was positioned in between the transmitter and the receiver, with its initial angle oriented at 0 degrees, and the radiation detected by the receiver recorded. As we rotated the polarizer, the measurements decreased until our last reading at 90 degrees, where the magnitude of the radiation detected was small. We expected this value to be 0, but speculated there may be radiation bending around the outside edges of the polarizer, which have not been polarized through the polarizer and able to be detected by the receiver. The final section of experiment 5 involved the receiver being oriented at 90 degrees and changing the orientation of the polarizer. When the polarizer was oriented horizontally and vertically, there was no radiation detected by the receiver. However, when the polarizer was oriented at 45 degrees, there was radiation detected, even though the receiver's axis was orthogonal to the transmitter's. Here, a quantum mechanical effect took place, where there was a probabilistic transmission of light through the polarizer. All the photons comprising the radiation are oriented vertically when emitted from the transmitter. Because photons can only be oriented either up or down, and not at 45 degrees, after passing the 45-degree polarizer, half the photons will be polarized vertically and the other half horizontally. It is these horizontally polarized photons that are detected by the horizontally oriented receiver. In experiment 6, we observed on a macroscopic scale the scattering of radiation in a crystal lattice as described by Bragg's law. The initial experimental setup consisted of the transmitter and the receiver facing each other with a lattice aligned parallel to the incident microwave beam. We then rotated the arm of the receiver until the greatest amount of radiation was detected. From here, we rotated the lattice 1 degree clockwise and the goniometer arm 2 degrees clockwise, and recorded the radiation detected at each step. Plugging our values into the Bragg equation to determine the spacing between the crystals in the lattice, we got the following values for each measurement. The measured value of spacing between the crystals was 1.5 centimeters, so there are some experimentally derived values that were similar to these expected values. We received an average of 3 centimeters for the spacing, and when removing outliers, received an average of 1.88 centimeters. The reason we got such inconsistent results for this experiment was that it was difficult to move the lattice and the goniometer arm just 1 or 2 degrees. It was a very small movement and difficult to determine if it was performed accurately, and trying to focus our eyes on such minuscule movements was straining on the eyes. Oh, the perils of being an experimenter.